Right, we are good to go. Good morning, everybody. Let us begin today's lecture on image processing, retrieval, and analysis with a recap of what we studied last time. And the reason that I re-emphasize the name of our lecture, processing, retrieval, and analysis, is actually that today we are really looking into sort of aspects of retrieval and analysis. Even though the lecture is called Image Processing, Retrieval and Analysis, most of the time we look into processing problems, but now we are positioned to look into retrieval and analysis. Analysis we've done earlier when we studied template matching and discriminant analysis. But to make a long story short, what was it that we studied last time? Well, we looked into the idea of local, what do we have here, image features, or computing local image features. Features according to Loewy's sift approach. And what we did last time is that we saw that this sift approach consists of 3 stages. And I actually called them stage 1.1, where we said the first thing we have to do when we are interested in Loewy's sift approach is to determine blobs on different scales. Right. I will not go through the computational steps once again, but just recall that when we talk about blobs, that refers to regions within an image that on different scales, or we may also think about them as looking at the image at different resolutions, appear to be blob-like, either bright, rather round spots, or dark, rather round spots. They may be elliptical, maybe almost square, but a blob is a component of an image that is rather homogeneous, and it may be smaller or larger, and that is the problem of scale. Is it a large blob or is it a small blob? We basically saw that we can think of the problem of detecting blobs in terms of operations that would involve the Laplacian, which we had to compute locally at every pixel of an image. We also discussed that instead of computing the Laplacian, we may simply resort to a difference of Gaussian operator, which is slightly faster. And speed is always a good thing to achieve or attain in image processing, especially if images are large. Most image analysis, image retrieval tasks, so the stuff why we would actually want to do this automatically does not really make sense if, say, we can compute several or have to compute seconds per frame instead of frames per second, because if the algorithms we devise are slower than the human brain, then it does not necessarily make sense to try to automatize tasks that can be done more efficiently by the human brain. So speed is always a good thing to get or achieve. Now, once we had computed these blobs on different scales, we can translate that or think of this as a set of key points, and this time they are not quarters, as in the case when we studied the Harris descriptor. This time the key points are, I don't know, the center points of the blobs we found. We get the location of the blobs, and we also get the scale of the blobs. So we end up, after the first step in this processing pipeline, with a set of key points and scales. This is to say we are given a set, let me say it's from I equals 1 up to lowercase n of triples, xi, yi, and the scale is given in terms of the variance of a Gaussian. Homogeneous Gaussian has the same variance, we assume same variance in all directions. So that is what we get after processing step 1.1 in this pipeline. The second step, I call it 1.2 because it is still very similar in spirit to this first step. So instead of 1, 2, 3, talking about 1.1, 1.22, is that we next determine the blob or key point, I should say blob or key point orientation. Orientation. Well, that sounds daring. How can we determine the orientation of a blob? It's basically, indeed, somewhat of a strange idea to be carried out, but we always can look at these problems from a very pragmatic point of view, and the pragmatic point of view, for instance, would suggest that we do this from local gradient statistics. Local gradient statistics. Well, and whenever I use the word statistics, there's two possible meanings attached to it. Either it refers to the mathematical field of statistics, or I use it in the sense of computing a statistical characterization of what is going on with a large set of something, typically numbers. And here, what we did, if you remember, is we look at the key point location and the corresponding scale. That is, we look at that image in our stack of images we have computed before this pipeline began at the corresponding scale. And there at pixel xi, yi, we consider a certain rectangular neighborhood, actually square neighborhood about that pixel, and within this local window we compute lots of gradients, x and y derivatives. From that we can get the magnitude of the gradient at each pixel within this neighborhood and the orientation. And we then turn that into a statistics, which in this case is given by a histogram. We just count orientations. They are of course binned into, what was this, 36 bins, and count how often does an orientation between, say, an angle of 20 and 30 degrees occur within this neighborhood. These counts are weighted by the length of the corresponding gradients, and we end up with a histogram. And ideally that histogram has a clearly defined peak, because then we would say the corresponding angular range of that bin with that peak would indicate the locally dominant orientation in that image we are currently processing. Of course, it may happen that there are several dominant orientations, in the sense that several of the bins in our histogram have a large value which is about the same. And in that case, we would simply clone the key point. So far we have location and scale. And we would now say double that key point. We would now have two key points with that location and that scale, but one of them would have this orientation and the other would have that orientation. So we have to clone key points in case there are several locally dominant directions in the image, and therefore after this step we end up with a set of key points and scales and orientations. And so therefore we are now dealing with a set of quadruples xi, yi, sigma I, nothing new so far. And now fourth component is theta I, the angle that indicates the locally dominant orientation. And because of the possibility of having to clone key points, this may actually be a larger set than the set we determined previously. Alright, so this time I ranges from 1 up to capital N, where that capital N may be larger than the lowercase n we saw earlier. Now, after these two preparatory steps, we are then positioned to try to characterize what is going on in the image we are currently considering in the neighborhood of each of the key points we just determined. And this characterization happens in this second step of this approach. Here we determine a local feature vector. And that is to say, and again, it's basically a statistic about local gradient orientations. Now, I'm not going to repeat this, but what we end up with is that for each key point, there will be a 128 dimensional vector, and that is to say a histogram of 128 bins, a histogram of relative, I did not really stress this last time, but let me stress it today, local gradient directions, and relative is to say with respect to the local orientation theta I we determined in the previous step. So think of it like this. We have determined the key point location and the key point scale and the key point orientation, and we then again look at the neighborhood about this key point and again compute local gradient directions and magnitude in this neighborhood, and again bin all this into a histogram and do some normalization and some thresholding. However, each of these histograms we compute in this feature extraction step is of course determined sort of with respect, we are interested in orientations of gradients, and they are of course determined with respect to the x and y coordinate axes of the image. But we know that this key point has a certain dominant direction, so we may add it to each of the angles we compute, and sort of this causes the angles we compute to be rotated, right? Rotated such that the local orientations we would obtain in this step are with respect to the locally dominant direction. Right? And that is great, and the reason for why this is great I shall point out now. Yeah, and you know, I made a lot of fun about all of this. This is really just my personal taste. I consider it to be unnecessarily involved or unnecessarily elaborate, but it really works extremely well in practice for quite a range of practical problems, and we'll look into some of them right now. And we actually begin to look into that by looking at the advantages of this idea of computing key points and then computing key point descriptors or key point features the way this approach suggests it to do. Well, first of all, we have translation invariance. Well, this is easy to imagine because for the kind of feature vector we computed here, it really doesn't matter if we compute it somewhere, say, at the upper left-hand corner of an image, or if the image is translated and the object previously seen in the upper left-hand corner now is in the lower right-hand corner, we compute the same pipeline, it doesn't matter. None of the processing steps we did here when we compute the local features depends on the location in the image. Of course, we compute them at a certain location, but the features of that location are independent sort of the x and y coordinates. We just look at local gradient statistics and whether they are computed, say, in the upper left-hand corner, lower right-hand corner, doesn't matter. If the image looks more or less the same in both areas, then the feature vectors will look more or less the same. So in that sense, we have translation invariance. We also have, not really, but about scale invariance. And to illustrate that, let me draw you a picture, or actually two pictures. So two pictures, and well, let's say it was the picture of a cat, and yeah, let me actually introduce some translation here. So it's two images of the same cat taken, say, after at two consecutive or two different points in time, image 1, image 2. Now, what are the blobs in these images? It's of course really didactic here. But we can, I guess, easily agree that, say, the ears somehow stick out. And given the way I have drawn these pictures, the ears are surrounded by something either dark or bright. They are blobs, local blobs. Right? So if all goes well, we get a key point here. And that key point, well, has a certain scale, which I will indicate by a box. It should have actually been centered about that key point. And it has an orientation, which I indicate by this arrow. Right? And we can do sort of the same process of key point detection in the second image, and maybe we find a key point here. And it has a certain scale, smaller this time, because the cat is, I don't know, farther away from the camera, whatever. And say it has, again, an orientation. So, if all goes well, and we really don't know that, but practical experience of more than 15 years shows that typically everything goes well. These 2 points would end up with a 128-dimensional feature vector that is, which are very similar to each other. Right? It's very unlikely that they are exactly the same. That never happens. but the feature vector we compute here will be very similar to the feature vector we compute here. And this is to say that we have scale invariance, because here the object is a bit larger, and sort of the blob for which we can establish a correspondence across these two images, in this case the left ear of the cat, appears at different scales. But given the way these features are computed, there is this scale aspect in computing the histograms of the local gradients. Given the way the features are computed, the two descriptors will be very similar to each other. So that is to say, in this situation, let me call this one here point 1, and this one is point 2. Then we typically find that the vector, and that is to say the histogram, of gradient orientations will be similar for key point P1 and key point P2. This is great, and it has been designed like that. This whole approach has been designed to be more or less scale invariant. We also have about rotation invariance. And again, let me illustrate that in terms of two pictures. So again, say the cat. One image looks like this, and the other image looks like so. So the cat has head tilted to the left and to the right in these two situations. So it says 1 and 2. Again, we would hope that dominant blobs in both images can be determined. So again, let's go for the ears. They have a local scale and a local direction. This time the scale is comparable, is about the same size, but the orientation now is considerably different. Again, that should not matter with respect to the feature vectors we compute from these key points at a location with a certain scale and a certain orientation, because these features are computed relative to this orientation, and therefore whatever we compute at point 1 and at point 2 will again be similar. So you know what, I don't have to repeat that sentence. It applies to both situations. Well, this is, again, I said, incredibly elaborate. And I'm mocking it for that. But I really shouldn't, because maybe you are now tempted to think, well, you know, we can have that easier. Computer vision is really very difficult. And one way how we can immediately see that, even without knowing anything about computer science and algorithms and signal processing and the like, is to consider the fact that the idea of computer vision, that is the general idea of having machines that can see just as human beings can see, is of course nothing new. Has been investigated ever since the late 1960s, early 1970s. So for at least something like 50 or 60 years right now. And the fact that these machines are still not out there in our daily lives, still not consumer level products, is very revealing. Of course, we nowadays have computers and, or say, even consumer level cameras that can detect faces and just take a picture when every person visible in current scene is smiling or stuff like that. So computer vision is beginning to diffuse into our everyday lives. But the fact that it is not really present yet, even though it has been researched for 50 to 60 years, with extreme efforts of time, person years, and money, is revealing. Right? If it was so simple, we would have it. Because everybody obviously immediately sees what we could do if we had machines that can see as humans or as people can. So yeah, lots of money, lots of time, lots of brain power has been spent on that, and there has of course been progress. But that progress was surprisingly slow. It is currently accelerating extremely. So yeah, honestly, I would not have thought to see the day while I am still active, where we have computer vision deployed at a large scale in our everyday lives, but I will now see it. It's just a matter of a couple of years now. So I have been making fun of this because I consider it a bit elaborate, but things are not that easy. If they were, the world would be different already. Computer vision is really, really difficult. And so therefore, approaches that have been tried are fairly elaborate rather than trivial or simple. And so therefore, bottom line, don't take it too much to your hearts if I'm poking fun at this. This is actually, it is a really, really good idea. And it works really, really well in practice. So let us see how we can use that. What to do with this. Now that we know that we can compute local characteristics of an image that are translation invariant, fairly scale invariant, and fairly rotation invariant. What can we do with that? So therefore, we now look into the idea of efficient image retrieval or object recognition. Using SIFT. And it may be, I don't know, appearing strange to you that I'm using retrieval and recognition, sort of the same headline here, but it's really difficult to distinguish what we are going to talk about now. Is it image retrieval or is it object recognition? Let's see what this is all about. So our setting is we consider a large, and let me stress the large database or collection of labeled images. That is, we are given many images, many pictures, and somebody has taken the time to annotate them. Nowadays, this is a fairly everyday situation because there are services out there such as Flickr, for instance, where there are many images. And the people who upload the images to Flickr very often tag them with, I don't know, sunset, red, beautiful, something like that, or even my cat playing with its favorite toy, whatever. Like, people like to share images these days and provide us or the world with descriptions as to what is to be seen in the images they upload to the internet, to the web. Now, that has not been the case for all eternity. It is a fairly new phenomenon, but really nowadays this is given. If we want to, we have access to large databases or collections of images where we have labels for the images. And in addition to these labels, which I obviously implicitly thought are words of the, in this case, English language, we also assume that for each of these images we have a corresponding labeled set of SIFT features, or I say SIFT descriptors. And again, this is, best illustrated by means of an example. Let's look at our image database. Actually, we only look at the first 3 images in the database. Of course, there are many, many more. This is image 1, 2, 3. Here we have, what do we have? A cat. Here we have a dog. And here we have some scenery. Some tree. Some scenery. These are different kinds of images we can think about. We can think about the fact that for each of these images, key points have been determined. So local blob-like structures, I'm just sort of indicating some of them, whatever. It doesn't really matter where I draw these red dots. And since there will be a lot of key points in every image, we have a set of key points for every image. Let me indicate it like this. It's a set of pairs, x1, 1, where the first component is actually now the SIFT feature vector. We don't really, maybe it's the SIFT feature vector together with the location, scale, and orientation. But this is definitely, this is something that really don't, I should be precise. So don't throw away information, right? If you have computed the locations and orientations and scales of the key points, keep them. But for what is to follow, we are mainly interested in actually these feature vectors, these 128-dimensional feature vectors. And this first component here in this pair, it's still, let me close it, so this is going to be a pair of things. First component in this pair is this feature vector, maybe with 4 additional dimensions indicating location, scale, and orientation. That's not really bad yet. It's the first component, and the second component is a label. It could, for instance, be cat1, and of course there will be another key point for this image, but it may also be labeled cat1, and so on and so forth. Here we have a second set of key points and labels. So this is x1 in image 2. Let's say this is dog, I don't know, 2. It really doesn't matter, these are just some labels. This is feature vector x2, 2, dog 2. This is not exponentiation, right? This is just counting. So on and so forth. And then here for this one, we would have once again the same situation. Let me x1, 3, and I call it scenery. And it's scenery 3 because it's our third image. Again, this is just, doesn't matter. what we have in the end is many images, and for each image we have a set of pairs, where in each pair we have a feature vector and a label for what that feature vector indicates. And in total we therefore have a very large set X, which is the union I ranging from 1 up to, I use capital N here, these local sets, or local, say, image-specific sets. Now, I don't know, for whatever reason, I do not use that term, which I want to talk about now, in my notes at this point. But let me provide you with an analogy. Instead of images, we could think of this, now has nothing to do with image processing, or just superfluously. Can think about this as texts, documents, books. Say, right? We have a large database of books, or say HTML pages for that matter. And do you know how Google finds resources on the internet if you enter something into the Google search engine?
Inverted index?
It has an inverted index. This is great that you know about inverted indices. What is an inverted index? Okay. Working with images is difficult, is really difficult. Working with text is not trivial, but somewhat simpler. And the problem of having to look up texts in a huge collection of texts, or finding documents that are relevant with respect to a query, is a very old one. You know, like, again, it's nothing new. And there has been tremendous progress in the area of text retrieval, or as it is sometimes called, information retrieval, which is exactly the problem setting where you enter a set of keywords, look at it, keywords, key points, keywords, into a, say, search engine, and it returns a list of documents that are relevant with respect to the phrases or terms you entered. And the way this is done in information retrieval is typically the following. We are given a lot of text documents, let's say HTML pages on the web, like, and there's billions of them, right? And for each of these pages, we can look at what kind of words do they include, what kind of words do occur on that page. And we don't really care about the order in which they occur. Just, is the word, I don't know, say lesson contained in that document or not? And if it is contained in that document, we can create an index entry. We could think of first coming up with a large vocabulary of terms. Terms can be everything, like, you know, every word you might be interested in: lesson, school, education, bank, money, what, like, you know, lots of I don't know, running. A vocabulary is just a large collection of words. And we would agree on a vocabulary, and then for every of the text documents, we would index them in the sense that we check if any of the words in our vocabulary occurs in that document. Maybe we are actually as generous and just do not look for occurrence, but actually look at frequencies. How often does it occur in this document? And we would create well, a dictionary data structure, just as in the Python sense of dictionary data structures, where we have a key, and the keys here are the words in our lexicon. And for every key we have certain values, and these values in the case of text retrieval would just be pointers to all the documents in our collection of documents in which, say, the word lesson occurred. So lesson is the key in our dictionary, and then there is a list of documents And each document in this list contains the term lesson somehow. And it can occur in arbitrary context, but lesson is contained in that document. Let me, why just talking about it? A picture says 1,000 words. Let me keep that. Let me keep that. So what we have when we do text retrieval, this is our dictionary, and here is, I don't know, the word lesson, and lesson has a list of doc 15, doc 21, and so on and so forth. So millions of documents, but each of these documents contains words. We count, just determine which of the words occur in the document, or how frequently do they occur in the document. Then somebody searches for lesson and say university, I don't know, maybe down here, university, and here we have doc 15, doc 16, and so on and so forth. Not document 21 though. Somebody enters the search terms lesson and university into the Google search engine, and then Google goes through their index and actually looks up for lesson and university in which documents these terms occur, and somehow the intersection of these two sets is computed, and everything that is in the intersection of that is being returned. And they cleverly rank it. This is not of interest to us here. But this is basically how information retrieval with texts works, right? And yeah, I already said these are keywords. If we create a document, you know, this can be millions or millions of different words. The more, the better. Right? But if we have millions of words, they are called the collection of this is called the dictionary or the keywords, such as in key points. And we have, well, this list here. This is beginning to look similar, right? It's not quite the same yet, because we don't really see the index yet, and we don't really see sort of the inverted. Don't ask me why. This is called an inverted index. I really, and nobody knows why it's called an inverted index. It's actually an index, right? We have a keyword set to a list of things this keyword occurs in. We don't see that index structure yet, but what we see is that we can think of these things as words. Right? They are not words in the natural language sense, and actually they are called, how do I do this? Okay. I hope in your notes you can still do it. Somewhere there is space. I do it like this. These things are called visual words. This is because of this analogy to the information retrieval setting we ever so briefly talked about. So all these feature vectors here are called visual words. Well, not yet, but they will be called so in a second. And it's okay if you put that into the notes already. Right? Our problem is we are now given this huge collection of images, which we may think of a huge collection of documents, and we want to find similar images given a certain query. So let me state the problem. Our problem is that given a new image, or unknown image, I should say, unknown image, we may want to determine what kind of object it shows. Of objects it shows. That would be the object recognition problem. Or if there are similar images in the database, this would be the image retrieval problem. So you have taken a picture and I don't know, you want to know, does it have similar pictures? Are there similar pictures in the database I have? If that would be the case, if there was a collection of similar images, that would be great for you. You might not have to label your new picture manually, but you could just, reuse the labels for the similar images. Can be done automatically. It's great. This is probably a strange use case, but consider this. Where is image retrieval important? I don't know, say you were in marketing, come up with a great ad campaign and have a certain image in mind. Maybe you have one of your designers, you tell him about the image and they create a sketch. So I don't know, a young boy playing a ball on the beach because you want to invoke some happy feelings or something like that. And now you want to find an image that illustrates your mental picture of a young boy at the beach playing ball. Of course, you could have a large image database which is annotated, boy, ball, beach, stuff like that, and then look for all the images that are annotated correspondingly, search for the one that best fits your needs. But manual annotations, difficult. Somebody has to do it. Maybe there's the perfect image for you, but in that database, but it has not been annotated with boy, but like child, beach, whatever. So what keywords to search for when you do imagery is difficult, right? So people have thought about, can we do this automatically? So given an image, can we find similar ones? Say maybe you draw a sketch and then take a picture of that sketch and use that as a new image and want to determine whether in your database there are similar images. And if so, then it should return that similar image. You can say, this is exactly what I was looking for to illustrate my ad campaign. This is one use case for image retrieval. Yeah?
Will these tags or these labels come into play?
These ones are in a second, yes. Yeah, sure. Still trying to, create the bigger picture, and I know that I'm doing a lousy job. It's not really structured. What's in my head? I'm mentioning stuff as I go along here. These notes are a bit dated, unfortunately. I should have taken that. So yeah, this is image retrieval, right? But of course, you have taken a picture and you might, I don't know, if you upload it to Facebook these days, Facebook will automatically check if there are faces in there, and actually will also verify if the faces that can be found in the image correspond to certain people Facebook knows about. And if that is the case, then that picture will automatically be tagged and then added to the database. So that is sort of the object recognition problem here. Right. So this is the general kind of problem we are interested in. We are given this, lots of images. For every image we have lots of key point descriptors and labels for the key point descriptors. In total we have a very large set of that, and these very large sets are called bags of words. And that is actually all I wanted to say. So I was happily, I reached that point and then I deviated totally into information retrieval. That is just because I wanted to motivate why these things are called bags of words. Has nothing to do with words, but because of the analogy to information retrieval or text retrieval, they are called bags of words. So we are given a huge bag of words, labeled bag of words. And we want to use that for image retrieval or object recognition. And when I say huge, I really mean huge, right? This is tens of thousands, if not hundreds of thousands or millions of images. And in each image there will be hundreds of key points. So we have millions of images times thousands of key points. This is a large bag of words. So then, how can we do this efficiently? In addition, the words we are dealing with here are not words in the sense we find in text retrieval, where lesson or university are, okay, you may have misspellings, but typically these things are clearly defined.
There will be a lot of optimization we can do in layered, but
Yeah.
we are not seeing this thing.
Yeah, but we'll get there, don't worry. Like once we're done today, you know how to do it in Vision. So the difficulty here is that even though sort of we use it in analogy, we are not dealing with words. Words have a clear syntax, right? Our words are 128-dimensional vectors. But if, I don't know, we have two vectors and they agree in all their entries except for one, and the difference is just, 2. So we have 120 entries. And in all these entries we find a value of 100, just for the sake of the argument. And in one entry in vector 1 we have 101, and in the corresponding entry in vector 2 we have 99. Everything else is exactly the same. Then these two things are very similar, but not exactly the same. And in text retrieval, we can really rest assured that except for misspellings, which are being corrected automatically these days, everything is exactly the same. Lesson is written lesson every time it is written. Right? But a certain key point may have slightly different feature values in two different images. We have no, set is fairly scale invariant, fairly rotational, but just fairly so. Right? So there's this sort of uncertainty here. How do we deal with that? If we want to adhere to this bag of words idea, which works so well in text retrieval. So, our problem is new image comes in. Is it somewhere, does it have a counterpart in a database, or at least are some of the objects in that image, can they be found in some of the other of the images in our database? The idea for how to approach that is to compute local descriptors. For the new image and retrieve, here is the retrieve from image retrieval, similar, that is the difference between image retrieval and text retrieval, similar descriptors from the database and perform majority voting over the labels, thus obtained. Let me explain that. So, a new image comes in. We compute key points and SIF descriptors for this new image. We end up with a lot of feature vectors, and we have this even larger set of feature vectors in our database. This huge bag of words. And okay, now say we have computed 1,000 feature vectors for our image, the incoming one. 1,000 queries will now be done with the database. And say for every query we do, we look for the 10 most similar feature vectors in the database. So 1000 times 10 is 10,000. We maybe return or retrieve 10,000 feature vectors from the database. The 10,000 most similar ones to the thousands we have. Each of the feature vectors in the database carries a label or a couple of labels. But let's be, for the sake of simplicity, just one label. Right? So now we get 10,000 feature vectors, which is to say we get the 10,000 corresponding labels. Say 2,000 of them say cat, 1,000 of them say dog, 500 say scenery, and so on and so forth. Then most of the labels we retrieved this way out of our database say cat. And we would take that as a very strong cue that the image that just came in shows a cat. Right, that is the majority voting over the labels thus obtained. And we, of course, have to address this similar here. How do we do this? Pardon?
Cosine similarity?
Yeah, cosine similarity is always a good idea in this context. But this is actually a secondary problem if you think of it. What could be the major problem here? We are given, for the sake of the argument, 1000 feature vectors, and we have 3 billion feature vectors to compare against. Does that sound like a piece of cake, or can that be burdensome? This is difficult, right? Like it sounds not like a good idea if we were to do this in 2 for loops, where in the first for loop we loop over the new feature vectors we computed for the incoming image, and in the nested for loop we loop over the 3 billion feature vectors we have in our database. Would be 1000 times 3 billion things we have to do, and actually we have to compute similarity, so that sounds like a recipe for disaster, right? How can that be done efficiently with text though? So we have billions of documents on the web and a couple of keywords, lesson, university, whatever. How can we...
Hashing. Hashing.
Hashing is a good idea, yeah. Is it maybe a bit of an overkill here?
Sorting.
Yeah, sorting, and if we have sorted the stuff, then what?
Then binary search.
Yeah, so what the search engines do is they have this huge inverted index, right? But they split it, say, in 26 parts. Every word that begins with an A is stored on that server farm over there. Every word, no, it's like that. Every word that begins with a B is handled by a server farm somewhere else, and so on. So now in comes a query. First thing you check is what is the first letter, right? And you don't have to go through the whole list. You just pass it on to that part of your humongous distributed database that stores everything that begins with an L, say. Right? So you know, this is how they do it. And so therefore, instead of going through the whole list one by one, they just sort of go through a fraction of the list. It's, of course, a fraction is a bit of a euphemism here, but they just go through a fraction of the list.
But this might be problematic when this database is also dynamically changing.
Yeah, of course, things are way more involved than I'm making them to look here, right? No, sure. This is, no. It's a science on its own. Information retrieval is a science on its own. But we know that humankind, or at least a couple of companies on the planet, have mastered it. We know that, right? Because it takes a fraction of a second to get really useful results out of certain search engines. It is an extreme success and pinnacle of human ingenuity and engineering that it is possible, but it is possible, right? And of course these things are dynamic. Pages appear and disappear, and indices have to be updated. And in all of that, I didn't actually talk about the ranking that is also performed, right? But no, can be done. But there it can be done because, again, of the syntactic structure of words. Right? We know that if we have a keyword that begins with a Q, we probably should not expect to find documents in the part of the index where every word begins with an A. But here we are talking about 128 dimensional feature vectors. We cannot sort them. Think of that. If we had just one number for every key point, we could sort them. But vectors cannot be sorted. They are higher dimensional objects. There is no ordering relation for vectors here. What can we do? And you know, the fact that I'm discussing it like this, of course, already suggests that we can do something about it, right?
Hashing direction sort the hashes. It's quite handy.
No, hashing is always a great idea. It's always a great idea. And in fact, I've been working on hashes for vectors myself. So it's,
in the sorting idiom, we may sort them, like, for example, define the beans and compute the lengths of the vectors, and then, I mean,
yeah. I totally encourage you to come up with your own ideas. Right? So when I say, this is meant as an encouragement, but of course things are not that simple. People have thought of this for quite some time, and they have come up with the solution, and I'll show it right now. I was very happy when I actually saw that solution. I attended the conference where it was proposed. But come to think of it, so here's an efficient approach. How to address this problem setting we are just talking about. And it was proposed by Meester and Stevenius. And here's the shocker. Like, you would have thought, well, this is fairly obvious. Like, once you see it, it's fairly obvious. But it's actually just 10 years ago. Time flies, so 10 years ago is already like long ago. But this is nevertheless more than 5 years after the SIFT idea was born. Right? So it took humankind 5 to 6 more years to be able to do something, efficient with that. Now, let me just write it down and then we'll discuss this. The idea is to build a hierarchical like always sounds very efficient, hierarchical vocabulary tree. You already know why I am talking about vocabulary here, right? Because of, again, the analogy between what we are discussing right now and text retrieval. Using, and here is the idea, hierarchical k-means. This is best illustrated in terms of an example, a sketch, provide you with a sketch, but of course I cannot draw 128 dimensional, so let's look at a 2D example where the k in k-means is set to 3. Now, here's our example. I need, I'll do it like this. I need some more space. So a 2-dimensional space, of course, that would be 128 dimensional, right? And in this 2-dimensional space, we are given all these descriptor vectors from our database. Right? And if now, I don't know, a new point comes in somewhere here, we would have to check which of the given ones is closest to the one that just came in. So this is the query point, so to say. Which of all the given ones is the one we should consider to be most similar? Of course, when I say most similar here, then this can be understood in the sense of the Euclidean distance between that point and all the others, and the other point for which that distance is smallest is most similar. All right. And again, this is if that is done naively, we'll have a for loop over all the points we are given, and we can just compute the distance. It doesn't make sense. Doesn't make sense. Do you have already dealt with this problem of similarity search in high-dimensional spaces?
Yes.
Yeah.
Big data science.
Yeah. What did you do there?
Well, we at the end we discussed a lot of solutions, but
Yeah.
then the most practical was locality sensitive hashing.
Okay. Okay. So you will sort of learn the pragmatic approach people in computer vision like. You know, computer vision is always very pragmatic. Of course, we can think of, for instance, building a KD tree. Have you ever heard of KD trees? Yeah, can be done. Unfortunately, 128 dimensions is sort of at the boundary of what a KD tree can reasonably do. It's a data structure that will actually allow us to do efficient searches in these spaces, but the quality deteriorates with growing dimensionality, and 128 is exactly sort of in the range where it is not useful anymore. Now, Nista and Stevino said, well, let's cluster this. And in my example, I use 3 clusters, right? So I don't really know, but let me just draw some cluster centers. So this one, maybe I really don't know. I can care less. This one and here. I should have drawn it more Gaussian, but anyway. So these are the 3 cluster centers. And of course, so every point that is closest to this one is assigned to this cluster, whatever. If we have a couple of points in a higher dimensional space, and I'll be talking about this in great detail in the pattern recognition course. This induces a Voronoi tessellation. Right? By that I mean, in our simple setting here, we could think of these 3 prototypes, cluster centroids, however you want to call them. They partition the space into, in our case, 3 regions. And that was the first round of k-means. And then I said hierarchical k-means. Now, by that I mean, and I'll just do it for one of the Voronoi sets, because otherwise the picture becomes nasty. And let me choose this one here. So we now have partitioned all the data we have into 3 subsets. For each of the 3 subsets, we repeat that exercise. So let us partition this into 3 subsets. I don't know, there might be cluster center here, then maybe here and here, right? So that would probably give us something like that. And you know, this is of course not the correct, looking at that is actually horrible, but you get the idea. This is not the correct Voronoi tessellation, please. But what can I do? And then finally, let's do it one more time. So I don't know, here, whatever. So we would get something like this, right? So in our example, we have chosen k to be 3, and the number of levels. L is 3 as well. Now, how can we use this to efficiently decide similarity for our incoming query vector? Say it was, you know, our query is here. We do the following. Instead of comparing the incoming feature vector to all of the feature vectors in our database. We just compare it to the 3 cluster centers on the highest level of the hierarchy, and it is closest to this one. Now, then we compare it to the 3 cluster centers on the next level of the hierarchy with respect to this cell, and it's closest to this one. And here again we compare it like here. So in just 3 steps we ended up in this cell, and then in this cell we can do exhaustive search. Right? That's smart. That's smart, isn't it? I was so happy when I saw that. And it's really like, once it is there, it is there. You just ask like, why hasn't anybody seen that before?
How reliable is k-means?
Let's discuss that later. It's a very good point. It's a very good point. But let's not look under that rock right now.
Sorry.
No, it's like, it's brilliant. Very good question. So this creates a tree, right? Let me draw this tree. This is the root, and then we have in our example 3 successors. And for each of these successors, we have 3 successors. And for each of these 3 successors, we have 3 successors. I should not do this, but I did it anyway. Right. And then for each of these successors, we have whatever. Either a lot of individual points, or we might even say, you know what? We don't really need to know whether we are. So we really know now we are in this cell here, and there is, say, 20 more points we could check against. Maybe we should do this. Maybe we don't. Maybe it is just sufficient for us to sort of store in this tree that, let's say, I don't know, what happened here is we came this way, like so, and then so. Right? That is sort of the path this point took from. And then, say, in this cell there are 20 of our database vectors, and 2 of them are labeled cat. One of them is labeled dog, and one of them is labeled scenery, and so on and so forth. So, if we follow this idea, we have 1,000 new feature vectors computed in a new image. For each of these feature vectors, we propagate them to the root level of the tree. Either we look for the closest one here specifically, or we ignore that, but just sort of collect the labels of all the points in this cell at this leaf node. So here we would find cat, dog, scenery, whatever. We do this for another point. We end up with cat, dog, cat, scenery, and so on and so forth. We do this for all the 1,000 feature vectors we have, and we just count sort of what was the most frequent label. And if that was cat, we would say the new image, the one we are currently analyzing, shows a cat. That's it. That's it. Right? And you see now that I did not really distinguish between object recognition and image retrieval here. This idea can be used for either case. We can, instead of using the object labels here, we could have image numbers. Say image 1, 1, 1, 2, 5, 5, 5, 1, 1, 5, 2, and so on. So then a new image could come in, and we would just look at like what was the most similar image, not the most frequent label, but the most frequent image number on this lowest level of the pyramid here, right? So yeah, there you have it. Let me see if I have something else.
How we determine number of levels? Because
okay. Yeah. Now that you asked, then let's go for that. I was. You asked for it, so 10 more minutes. Anyway. So I don't, have to write down.
Is
like
it
this.
a logarithmic scale? I mean, just asking by maybe the number of k's we have, and then just log base k to the number of all images.
These are questions nobody can answer. So, but what I can say is that this requires L times K comparisons. Right? Like every, we have L levels, and every level has K prototypes. And Niester and Stevenius, said, don't ask me why, L equals 6 and K equals 10. Works. Works. Right? It works. And of course, once it was there, people began to tweak it, and I was really, it's so obvious. It's so obvious. Before I address your k-means question, let me...
so it's 1 million bits, basically.
Yeah. Yeah. Who cares? Huh?
Round number.
Yeah, no, why do they set L equals 6 and K equals, who knows? Does it make sense? Who knows? Does it work? Yes, perfectly. Their application was an image retrieval application. So they were dealing with CD covers. Right? So they had a database of CD covers, lots of them, music. And then they had a camera, and they just, put a CD in front of it. Some, rotated, far, close, whatever. And I just wanted to know what CD is that. And it was rotate, so it was a retrieval problem. Like, is there an image in our database that is similar to that? Of course, not exactly the same, but because in the database they are all perfectly orientated, and in front of the camera they are, whatever. And they could do this in a fraction of a second. Like, seriously, like this can be done. This actually allows to process frames per second rather than to run seconds per frame. This is extremely fast. Yeah. I'll get back to k-means. I'll really get back to k-means in a minute. But let me say something more about information retrieval and some more tricks that may come in handy here. So the question is, how relevant is an image in the database? So determine the relevance of database image with respect to query image based on how similar their distributions of leaf nodes are. This is another instance for the world is more complex than I often make it to look like. When we looked at this, I said, let me just count which of them appears most frequently. Cat, and it's cat, right? But if we are dealing with a situation where we would have, I don't know, lots of scenery images and a cat playing on some meadow, then it is likely that in that image most of the key points we extract may not actually be located on the cat in the image, but in the background, meadow, trees, whatever. And so therefore, we may actually end up with this approach returning lots of scenery images just because the cat is, playing out in the garden, and it would be labeled scenery rather than cat, because the majority of the key points would indicate this has to do with nature. This is not so good. This is not so good. The problem in text retrieval is easier to understand. Most texts you will read will contain words like the and of and so on and so forth. Right. This will basically occur in every document. But the information content of these words is almost zero. Because you cannot distinguish content just from counting how often the word the occurs in a document. These are called stop words, right, in text processing. Do we have stop words in visual search as well? Well, yeah, most likely. Right. So in information retrieval or text retrieval, there is the question of, so certain words may occur really, really infrequent. But if they are there, then they are a very strong cue for what is going on. For instance, let me just come up with the word surgery. Right? This is it hardly occurs in your everyday reading of stuff on the web. But if you read something that contains the word surgery, it's almost certain what this article is about. Right? So that is a question: can we do something about it? Can we sort of assign weights to reflect the importance of certain words? And it can be done, and again, it had been done 20 years earlier in text processing. And here is how it translates to our scenario. So for each leaf node, and I call it I, we define a weight Wi is given by the log n over ni, where n is the number of images in the database. And ni is the number of images in database with at least one descriptor in node I, which is a leaf node in this tree here. That still does not make a lot of sense, but it will in a second, and we'll get back to your cosine similarity. So we now have computed weights for the leaf nodes. And we use these weights to characterize the query image. Query image Q and database image D as follows. As you said, we now have 1 million leaf nodes here. Right? And we collect them in a vector. So million-dimensional vector doesn't matter. We just say the I entry of if we let all the features of the query image diffuse to the bottom level here, that gives us a vector for the query image, and its ith entry is given by ni times this weight wi, and for di we have mi times wi, and ni, this is should have used a different n here, but here ni, I should have so I used ni on the previous whiteboard. All right, I still can correct that. So mu I and mu I, and here this mu I and mu I are numbers of descriptor vectors of Q and D respectively. Right? That is to say, I don't know, for one of the images D in our database, which we now represent in terms of a vector, for that image we had just 10 key points. Right? So that corresponding mu I would be 10. And for the query image we have computed 1,500 key points. 1,500 feature vectors, so that would be this new I here, larger number. And if we have defined these vectors like that, we can then compute a similarity between these vectors. The similarity one way of doing it is actually looking at the similarity between image Q and image D, and we could define it as this vector Q over its norm minus the vector D over its norm, and we take the absolute value of that. This is not exactly the cosine similarity, but it is a sort of similarity. You could, of course, also use cosine similarity here. Now, all I did this for is to say, and then we're good, that this realizes a TF IDF scheme. And that is another term from the area of text retrieval. It is an abbreviation for text frequency, inverse document frequency. Okay, and given the manner we defined these weights, we now actually could deal with a situation where we have a visual word that is really rare. In the sense that hardly any of the images in our database contain that visual word, but maybe it is really important in the sense that if this is there, we know for sure that this is a surgeon operating, for instance. Right? Can happen. And TF-IDF schemes allow to sort of trade off frequency versus importance. Words like surgery may really occur just rarely in our text database, but in the few documents they occur, they are really important. And even though there's just a few documents, these are really easy to categorize. And so therefore, if we were just to go for frequency of occurrence, then words like the, by, on, and so on would dominate anyway. So we remove these so-called stop words anyway. But still, there will be a couple of words that are really dominant. And using schemes like this, and here we cannot really see that, but it is in the way we defined this logarithm for the weights. That does the trick here. That does the trick that even if a visual word does not occur really frequently, but if it occurs, then it is important. That is captured now. Right? And so therefore, instead of just doing majority votes here, we can do more elaborate stuff. And let me cut it here. This is actually not worth any further discussion. I have a lot of more stuff on this, but I will answer your k-means question in a second. But before I do so, I have a question for you. Now that we talked about local features and how to extract them, and how to extract them in a robust manner, robust against scale, rotation, and translation. And then we discussed how to use them for object recognition. This is just one example. Can you now imagine that if you think back the lecture where we discussed tensor LDA for template matching, and I said we can do this really fast and we can achieve 88% recognition accuracy, but there is a method that is much, much better. Could you now imagine that there are methods that are much, much better? Right? Approaches like these, and this is why these bag of word approaches that are based on the idea of extracting key points and local features, are so popular because they are fairly robust against rotations, scale, distortions such as occlusions. Right? If not all the key points are there, it doesn't matter. If there, I don't know, should be 20 key points, but just 5 are there, you can still run this and still get majority votes or TF-IDF values, whatever. That doesn't matter. So no, these are really more robust than template methods. Right? It had been the gold standard in object recognition for the last 15 years. Things are changing now, but it has been the gold standard to look at local properties of images and treat an image just as a huge collection of words, such as we would treat a document just as a huge collection of words. Huge collection of visual words in case of the image. Right? And then do some elaborate either retrieval techniques, matching algorithms, machine learning, it can pattern recognition, doesn't matter. That's that. So yeah, these things are, this is just an example, and this is not what they used for the cars, but similar in spirit. These things are really, really robust against a lot of deteriorative conditions. Now, is k-means the best thing to do? No. Why is it done anyway? Simple. Do they care? They really don't. It drives me mad. It really does. To most people, clustering has become synonymous with k-means, and that is really unfortunate. Because k-means is a great idea, and it has beautiful properties and great statistical guarantees, but it also has very severe implicit assumptions. There are ideas built into that algorithm that are not obvious to the users, and k-means really should not be used in any situation, but it is. And I guess I'll keep it at this, right? No one is. But is it for instance worth? Okay, so say nowadays go through this idea and replace the k-means step by something else here and keep everything else and get better performance. Would anybody care? No. In 2007, maybe somebody would have, because you could say, yeah, this great new thing, I have made it even better. But it's like nowadays nobody would care anymore. Even though very likely you could get even better results if you were to use a more appropriate algorithm for the kind of data you're dealing with here. Great, that is all I have for today. Do you have any questions? If not, then see you next week. Thank you.